učiti, kao i mnogo komplikovanije analize. Svaka od tih stvari je teška na svoj način. Profesor Charleson je preko 20 godina, on je građevinski inženjer koji je više od 20 karijerom koje traje preko, ja mislim, oko 40 godina u ovom trenutku, prvo se penzionisao i proveo je otprilike polovinu svog radnog veka kao građevinski inženjer, a polovinu predajući arhitektima konstrukcije i posebno zemljotrusno inženjerstvo na univerzitetu, Victoria Universitetu u Wellingtonu. I penzionisao se prošle godine i sada želi da deo svog vremena u penziji provede predajući arhitektima na različitim fakultetima u svetu zemljotrusno inženjerstvo. Već je bio u Indoneziji ove godine, sad je bio u Albaniji, a odavde ide u Osijek posle nas i ima druge planove, tako da smo srećni što je došao i da sa nama podeli deo svog znanja. On je objavio 4 knjige, od toga jedna na koju će se pozivati, koja se zove inženjerstvo za seismic design for architects, znači seismičko projektovanje za arhitekte. To mu je stvarno poznato i udžbenik je na mnogim univerzitetima u svetu. Sa tim da pozovemo ovog profesora Charlesona, da ga pozdravimo i ovo će sad biti prvo predavanje, posle toga će biti pitanja i posle toga koktel ispred ovde sale. Eto, to je profesora Charlesona. Hvala vam.
Well, good afternoon, everyone. I'm going to begin my talk and try and speak quite slowly so you can get used to my Kiwi accent. Some people find Kiwi accents hard to understand. But it's been interesting because since I've been in the Balkans, everybody thinks I'm from England. But when I go to England, people can't understand me because of my Kiwi accent. So I don't know, I don't understand. So these are the topics for this afternoon's lecture. They are quite basic topics, but they're very fundamental to achieving buildings that are safe in earthquakes. And so to begin with, I'm going to remind you of the 3 structural systems that are suitable to resist earthquake. And I'm always amazed that there are only 3 systems that we choose from. And sometimes I think that because there are only 3 systems, that is very bad for architects because it limits their creativity. I mean, imagine if a painter has only 3 colours. They would be very limited. And so it seems that potentially it is very limiting for us. And so in some ways the bad news is just 3. But as we will see during this lecture, there's an infinite possibility of the way we use these systems. So as architects and engineers, for every building, we have to make a choice of one of these systems to resist earthquake attack. And usually, we may choose more than one system, but we try and use one system in one direction. And so in this direction and plan, we will use one of those choices. And then in the other direction at 90 degrees, we can use the same system, or we can choose another system. And so I'm going to briefly just describe the advantages and disadvantages of each system before moving on to my next topic. And I'm going to start with shear walls because, in my opinion, shear walls are the best system to resist earthquake. This is based on earthquake damage observations throughout the world. Shear walls have always performed best. Then I will talk about cross-brace frames, and then we'll finish with moment frames, which are probably the most popular among architects because of the openness and transparency and the circulation possibilities. But moment frames are the most sophisticated of these systems. They're the most difficult to build safely, and also that they're the most flexible. Before I move on to shear walls, I just want to say a few words about post and beam structures, or trabeated structures, and load-bearing walls. Post and beam structure, of course, is the oldest structural system in the world, and it is great for gravity loads. Beams and columns, beams and posts are great for resisting for gravity load. But if there's any horizontal load, this will collapse, won't it? It becomes a mechanism because of the pins. Load-bearing walls are also very good for gravity. But we always have to remember that when walls have loads in this direction, they are very unstable and dangerous, just like post and beam structures. So when I'm talking to you about walls or shear walls, I'm talking about the ability to resist forces in this direction. And I just want to remind you that these walls, they need support against this direction. So in one direction, walls are strong. In the other direction, walls are really dangerous. And they need support. And so here are the most common types of shear wall. This is the most simple. A standard structural wall, and it's always best if the wall starts with the foundation and it continues right up to the roof. Now, this wall has got no merit architecturally, has it? It's really boring as an architectural element. And Zaha Hadid and Toyo Ito would never design a shear wall like this. They would somehow transform it a little. Zaha Hadid, she would never design a wall like this. She would always design it like that, or like that. And that's fine. And so as architects and engineers, we can take something that is basically boring, but simple, and transform it so that it becomes part of a work of architecture. And if we want large openings in a shear wall, we more or less have to create a coupled shear wall, which means that we have special diagonal reinforcement if we are working with reinforced concrete. So what are the materials of shear walls? Well, I think you know the best material is reinforced concrete. Then we have reinforced concrete masonry. Then maybe we have confined masonry, which is the construction typology in this part of the world. And in my own country and in the west coast of the States, we have a lot of plywood shear walls. And so using plywood, these floors would be wooden floors, and the plywood would create the main component of the shear wall. And so shear walls can be of these different materials, but the main principle is that they start at the base and they're continuous up the height of the building. Then we move on to different types of cross-braced frames. And you can see there are different geometries of the elements. But basically, we are wanting triangulation, because triangulation equals stability. And so in the top row here, all the braced frames are triangulated. And they could be of any material, probably most commonly steel, but they could be of reinforced concrete, and they could be of wood construction. That would be quite common as well. And so they would be the main materials for these cross-braced frames. For light industrial buildings, this type of bracing is very popular, like for factory buildings, where we would have tension-only bracing. So the bracing members would be of small diameter, and so they're only capable of resisting tension. And so this is a reasonably suitable system for low-rise and lightweight buildings. And then in more recent years, we've moved to eccentric bracing, which is an unexpected move actually, because for the first time engineers are moving away from triangulation, and they are deliberately creating eccentricity, deliberately avoiding triangulation to create what we call structural fuses. How do you say fuse in Serbian? Is it an easy translation to make? And so the philosophy is that this is the fuse region. And during an earthquake, the damage occurs here and nowhere else. And the idea is, after an earthquake, we hope we can repair or replace these fuses. And so certainly in my own country, the most economical form of earthquake resistance is actually using these systems. They are very ductile because of the fuses, and structurally efficient because of the braces being inclined and becoming quite like a standard cross-braced frame. And there are several different typologies of this eccentric bracing. And engineers need to work with the architects to choose the most appropriate geometries. If we are using eccentrically braced frames, it's essential that the beam is steel, because the beam will get damaged, it will absorb a lot of earthquake energy, that will increase the damping of the building. So this must always be steel, but all these other elements, they could be anything. Reinforced concrete, even wood. No problem. And then we come to moment frames. which, as I said, are the most popular of all the structural systems to resist earthquake forces. But they are also the most difficult systems to build and design properly, because they're so sensitive to details. And so for a moment frame, the basic requirements are quite a deep column and a rigid joint between column, and we also need a strong beam. And so we have these very basic requirements. But what many people don't realise is that for a moment frame, it has to be designed to be effective in one direction, usually. And so if this is the beam, the moment frame will be strong in this direction. And therefore the columns need to be quite deep in the same direction. So the column orientation is really critical for a moment frame. Like this would be a moment frame in wood or reinforced concrete. If we were designing a moment frame in steel, the column orientation would have to look like this, with the column strong and bending and shear in this direction. And so this would be a very poor column layout for this moment frame, because the beam is in this direction, but the columns are strong in the opposite direction, which is almost useless. And so this would be a very weak and flexible moment frame, which would not perform well in an earthquake. And the same with steel. If we made a steel moment frame like this one here, like this one here, that also will perform very badly, because the steel columns are very flexible and very weak in this direction, the direction of the beam. And so moment frames require a lot of care at the preliminary design stage for the orientation of the columns, and to make sure that there's enough depth in the columns so that the frames are strong enough. Of moment frames. Well, reinforced concrete is a very commonly used material, but structural steel is very prevalent in some countries as moment frames, and also wood is quite is rather slightly common in New Zealand and other countries where wood is readily available. The problem with wooden moment frames is creating this rigid joint between column and beam. So that's my first and very quick introduction to the different structural systems that we designers have to choose from in all of our building designs. Next, I want to discuss the problem that earthquake attack is totally random in direction. You know, during an earthquake, the ground can be moving in this direction in 1 second, and in the next second it can be moving there, or there, or there. It's totally chaotic. And so it would seem very difficult for us to design our structure to resist a chaotic movement. So how do we do it? Well, we're really fortunate that it's quite easy. Let's say that the earthquake is attacking at this angle theta. That's the direction of the earthquake attack. Well, because of the theory of vectors and the theory of components, we can resist this earthquake attack by providing for strength in the x direction and strength in the y direction. If we have strength in both of those directions, the good news is that we can resist earthquake attack from any direction. And so we're really fortunate that this is such an easy solution. And so architects and engineers basically have quite a simple problem. Provide strength in the x direction and provide strength in the y direction. And then our structure can withstand attack from any direction. Because of the fact that we can take the component from any earthquake attack and resolve it into the x and y direction. And so when we come to think about the way we're going to configure or lay out our structure and plan, this is the first principle that we've got to satisfy. This is the number one principle. Provide resistance in two or both orthogonal directions. The second principle, and I think there are really only two principles, is we've got to design our structure to resist torsion. Because if this is the plan of our building, during an earthquake, there would always be some torsion, possibly caused by the migration of the earthquake waves under the site of the building. That can cause torsion. But more commonly, due to the fact that the centre of mass of the building is not identically located with the centre of strength or the centre of stiffness. And so we can assume that during an earthquake, every building is going to start twisting and torsion. So how do we solve that? Well, in order to solve that problem, we have to apply the second principle. And this is also quite simple, but it can be quite difficult. We must provide a minimum of two structures in each direction, and they must be separated like that, separated in plan to resist torsion. So if we are designing for an earthquake prone zone or region, we should always have a minimum of two structures, like two shear walls, or two moment frames, or two cross brace frames in this direction, and they must be separated in plan so that when the building twists, these elements can resist the twisting. And the same thing applies in this direction. we must have two elements, separated in plan to resist the torsion. And if we satisfy these two principles, we are well on our way to achieving a really good seismic resisting configuration. The best place to place earthquake resistant structure is on the perimeter of a building. That is the best place because it gives us the greatest distance that helps withstand the torsion. And so when we are thinking about a new building, that's probably where we should begin. We should discuss architect to engineer if it's possible to have our seismic resisting system on the perimeter. And if it's not possible, well then it still might be okay, but we have to come up with a different solution. So if this is not possible, maybe it would work to bring those shear walls closer. Maybe to have a structural core, maybe. And an engineer would be able to make that work. And so there are many different possibilities. And in fact, these walls, like this shear wall, it could be down here. This wall could be up there, because we've still got that separation. And so there's a lot of flexibility that architects appreciate in the way we can configure the structure in plan. Now I want to introduce the software to you. In order for you to be able to size your structure. I mean, it's all very well you making a decision. I'm going to use shear walls in this direction of my building. And in this direction of my building, I'm going to use moment frames. Now, you can easily make a decision like that, but the next problem is, how big are these elements? How long are the shear walls? And what material? And how thick? And so this is some software that I co-developed many years ago, and we updated in 2014. And you can use Google and find the software called Resist, and you can download it for free and use it for your designs. It's for preliminary design, and there's no calculations required. And all my architectural students use it. I'd be telling a lie to say that they love the software, but actually I think they like it because it's so easy to use. And so I'm going to show you the software, because in the process you will be learning new ideas about seismic design. And so the idea about using this software is so that architects can do the preliminary seismic design for their architectural projects. Because I believe it's essential that architects do the conceptual structural design. Because if you don't do it, the engineers will come along and impose a solution that may compromise or even destroy your architectural idea. Can you identify with that? And so my dream, my vision for structure in buildings is that it enriches your architecture. You know, structure is one of the most important architectural elements in architecture. And your job as architects is to use the structure creatively to enrich your design ideas, to reinforce your design ideas. And so that's what we're going to try and do now. So I just have to get out of this. Yeah, so I'm going to design a few buildings with you, and in the process you will be reminded of a lot of different structural principles, but in a way that we don't need to worry about calculations. And so we're going to design, say, a hospital building for Belgrade. And so we will choose post-disaster functions, won't we? We will choose the number of stories, I don't know, say 6 stories. This software only goes to 8 stories because any higher, the results are not reliable enough. Story height, say for a hospital, maybe 4 meters. The roof height, maybe, say, 4 meters. Then we need to choose the floor weights. And these are the different choices we have. A wooden floor, which is light. Steel construction, which is medium. Or heavy concrete construction, which is heavy. So let's say we're using heavy floors in this building, concrete. The live loads for a hospital, probably office would be close enough, I would say. The interior wall weights. If we've got brick partitions, they would be heavy. Let's say we're using lightweight partitions in our hospital. Exterior walls. Say we're using precast panels. They might be medium. There's information to give you guidance down here. Exterior wall weights are medium, and then the roof, say the roof is going to be a flat concrete roof, it's going to be heavy. So now we've told the software the materials. Now we go and define the floor plan for this hospital. And so, like this hospital building, maybe it's going to be like 50 meters, say by 20 meters. Now, the software has this default structure. And so we just, we'll just start with our structure being on the perimeter. We just drag these shear walls over there. Here we are. So this is like the default building. And then because we are architects, we would never want a hospital to be so boring, would we? So we're going to add some architectural interest to this hospital, and we'll add some points, and maybe create, you know, a more interesting architectural form. I mean, the civil engineers wouldn't do this, would they? But architects would definitely want to do this sort of thing. And so you can have quite a complex geometry if you want to. Oh, well, let's be a bit crazy. Let's do that. So there we are. That's our hospital and plan. Then we go to the earthquake, and you would probably go to the Eurocode and look up the Eurocode. I don't know, or you'll go to your Serbian code, your Serbian seismicity map. This is for New Zealand, unfortunately. And my guess is for Belgrade, I'm going to guess about 0.3 as being the acceleration for a 500-year return period. A bit smaller than that. 0.1. Okay, well, we're going to be very conservative tonight. Oh, well, I'll compromise. I'll do 0.2. Then we choose the soil type. What would be an appropriate guess? Well, I guess for new Belgrade, you'd be soft soil. Now we've put in all the information for the seismic design, and then we need to design for wind load. But I suspect that wind isn't really critical in Belgrade. Could be. All right, well, you would go to your wind map. You would go to your wind map. As I would in New Zealand, I would have to go to my wind map. And I would put in the wind speed and the terrain, and say our hospital is in the suburbs of Belgrade, suburban. And the topography, let's say it's on a hill, and say that the slope of the hill is quite low, maybe say 15 degrees slope. And the elevation, what's the elevation in Belgrade?
Around 200 and under.
Exactly.
Okay, you go with 10.
There we are. We don't want an argument. Okay. So now the software can calculate the forces on our hospital. So now we come to the X direction. The X direction, and we choose what structural system we want to use. And we've got the three choices. We always come back to the three choices, unfortunately. Nobody can offer you more than three, really. And it's always best in your designs to have one system in each direction. Try not to mix your systems, because if you mix your systems, the forces get confused. They don't know what system to go down. And you can't design the building very easily. So it's always best one system, one direction. And so this is where we have tremendous flexibility for example, as architects. Like in the X direction, we've got only 3 choices. Shall we use shear walls in the X direction? Oh, sorry. Shear walls. So the question is, how many walls? We could just have 2 shear walls if we wanted to. And the walls, they can be, we can place them to suit the architecture. Or we could have more walls to suit the architectural program and to suit the architectural concept. Say we have 4 walls. Say we believe that these 4 walls are best for the program and best for our architectural idea. The next question is, and we put these walls in plan, the next question is, how long do they have to be? And so we have to guess. This is preliminary design. We have to guess. Even an engineer has to guess. And so I'm going to guess, say 6 meters. Do you think that is enough structure? Incidentally, this is what a concrete shear wall looks like. We shouldn't have penetrations near the bottom, but it's okay to have them near the top. This is what a reinforced concrete masonry shear wall looks like, and this is a plywood shear wall. Okay, well, let's say as an architect, I'm really thrilled with that design so far, and so now I'm going to design in the Y direction. And in the Y direction, let's use moment frames, just for fun. And so this is what a moment frame can look like. I'm really embarrassed to say this moment frame is, this is a building from my own campus in Wellington. And I've never seen such a boring moment frame, right? This is terrible, isn't it, from an architectural point of view. But structurally, the civil engineers love it because it's regular and it's on the perimeter. So it's quite a sensible structure, but it's got no architectural merit. So our job is to decide how many moment frames we want. And we've got an infinite range of choices. If we wanted to, we could just have 2 moment frames in our building to resist all the earthquake forces. And that would mean that, of course, we would have a lot of columns and beams in the body of the building, but they would just resist gravity load. And we could design this frame and that frame to be the 2 elements that resist earthquake. It's our choice to make. If we just have 2 frames, the members are going to be quite big. And then we have to choose how many bays per frame. At the moment we've got 2 bays. But you see, we could just have 1 bay frames. Or we could have many bays. And we could reduce the bay length like that, you see. And so I think you can begin to see we've got so much flexibility in the way we can configure the structure. And so the architect is always thinking, you know, what is the best configuration for my program and my concept? And you use the software to test your different ideas out. And then you choose the one you're most happy with. I don't like this design at all. So we're not going to do that. We're going to have just a few bays, maybe 3 bays, and we're going to have a longer bay length. Yeah, say about 5-metre long beams. So we go to the floor plan and we just tidy that up a little bit. And so now I come back and I look at these frames, and to my New Zealand eyes, these columns look too weak. They look far too weak, and because I've only got 2 frames. And the rest of the structure, remember, is just resisting gravity. And so there'll be many, many columns in the plan here, columns and beams, resisting the gravity loads. Resist doesn't design the gravity structure. So anyway, I don't feel happy with these small columns, and I'm going to increase the size to make them a lot stronger. And I'm basically copying this, aren't I? So please excuse the architectural features here. So let's say I feel happy with this. Then we go to results. And if we see any red, we know we've got problems. Like I'll just talk about this. This is for the moment frames. This is for wind loads. And so this is for the shear force in the members. They're at 32% of the shear strength of the beams and columns. No problem. The bending moments in the members under wind are 37% of their capacity. No problem. And the drift means the horizontal deflection of the building. That is 62% of what the code allows. No problem. We've got 2 categories, the ultimate earthquake and the serviceability earthquake. Like this could be ultimate and small earthquakes. And for both of the earthquake scenarios, we've got problems because the shear forces are greater than 100% of the code allowable. The bending moments are greater and the building is too flexible. It's drifting too much. And it's even worse for the small earthquakes. So this would mean in a small earthquake, the building is drifting a long way, and there would be a lot of damage to architectural elements. Like all the walls would get really badly damaged and have to be replaced, most likely. So I've got a problem here. My structure is too weak and it is too flexible. And I've also got a problem with my shear walls. They are okay in shear and moment, but they're too flexible. The drift is more than 100%. And so I've got a number of choices. I can make the members bigger, or I can add in more structure. And so we can choose. So initially, for the moment frames, incidentally, this is what a steel moment frame looks like. I see the rigid joints. And this is what a timber moment frame looks like, where this is a method of creating a rigid joint between column and rafter, or column and beam, in a very simple building. So anyway, I'm going to increase the size of these members and see if it becomes ridiculous or not. It's becoming a bit ridiculous. Done. What does it look like? Horrible. Looks terrible, doesn't it? No architect would want that, would they? Please say no. So this is not a good solution. So what am I going to do? I'm going to put in more moment frames and reduce the dimensions. So I go back here. I first of all actually go to the floor plan, and I right click and I'm going to add in quite a few more moment frames. And because this hospital is being designed by a famous architect, see how the moment frames are offset? Because this is in keeping with this architect's brilliant design concept. There we are. The concept is about offset, okay? About sliding and shifting. So let's look at our results. They're quite low, and so now we reduce the sizes of these members. And we come down here. There we are. We still need pretty big structure, don't we? Remember, this hospital is on soft soil. That makes a huge difference. Like, if this hospital was on rock, let's just see what happens. We're at 99%. If it's on rock, and we can reduce our member sizes to that. So now our frames, are looking a lot more reasonable because this is assuming we've got better soil conditions under our building. So now we have completed that design. And architecturally, we're quite thrilled because the columns, we've got this very nice shifting pattern here. Let's go to the shear walls. We're on rock again. The shear walls are still too flexible, and so I can make the shear walls longer. Let's try that. Now there's 6 meters, 7 meters, 6.5. Okay, now they're fine. Also, I noticed the shear walls are not working very hard in shear. So I can reduce the thickness, say to 0.2, and maybe 7.5 meters long. So now our 3D model looks like that, and I finish the design. But then, you know, maybe on reflection, I think I've really got too many shear walls, and so I'd rather not have so many. So we go back to the floor plan, and we just right click. We just want to delete that shear wall because we want more transparency in our hospital. You know, we want maximum daylight for the patients, and so we're just going to have 2 shear walls now located there. And oh, we've got a problem. See the red flashing light? That always tells you there's a problem. And the problem is that there's a problem with torsion, because our walls, they are not far enough apart to resist the torsion. And so we just have to make an amendment here. We've got to unfortunately just move the walls a bit further apart, like that. We still have a bit of a problem. I'll just there's a slight bug. It says the lateral separation in the X direction is 66% of the building width, which is acceptable. So actually that shouldn't be flashing. So we'll just ignore that because we've been told that it's acceptable. And we will just look at solving this problem of the drift. And so if I need to increase the length of these 2 walls, well, 8.5, and just make the wall a wee bit thicker, say 0.22 meters, and there we are. So now we've got all our structure under 100%, and so we have finished our design, and now we have a building that, you know, meets the codes, and we finished our preliminary design. And as an architect, we are satisfied with this design. Then we would take it to the structural engineer to do detailed calculations. But we would know that we would be preserving and protecting our design concept, because that is so important for us as an architect. I'll just, what time, how are we doing?
6:30, but then we put some questions.
That's right, so just a few more minutes to explain a few more features for you. Let me just show you what the cross-brace solution is. Here's the cross-brace solution. I can just switch off the roof to make it a bit clearer. You can see we've got a steel solution. If we use eccentric bracing, and we can adjust the bracing size to make the braces a bit stronger. And let's see how that works. This is with the steel bracing. That works fine actually. So I've been a bit conservative. I can reduce the size of the braces. And there we are. That's our design complete for a steel brace solution. And so I hope that you will use the software just to investigate all sorts of options that are available to you. And you know, as always, keeping in mind your program and architectural idea, because both of those you must try and preserve as much as possible. You want the structure of your building to reinforce your design concept, and also to give your building the best possibility, you know, of meeting the client brief. When you use Resist, there's quite a lot of information here in the help section. There are some manuals and a step-by-step tutorial to help you. And there's even a video on YouTube. If you Google Resist software, you'll see a video basically showing you how to use the software. So using it enables you to try out different options to meet your architectural objectives. After we've done a design, and certainly for my own students, I ask them to print out a report. And so for the architects, architectural report, I think this is a 2-page report with very little figures, basically just giving the results we saw earlier. And before you print the report, you go to the model and you just orientate it so that you can see the structure clearly, and you just click on image and you say set image for report, and this image will be printed out on your 2-page report. For the civil engineers, they click engineering report and they get, I don't know, a 20-page report. And they're so thrilled with it because it's full of figures, lots and lots of numbers, and they look at those and they just feel so happy. They've got those numbers that gives them security and just makes them feel good. And these numbers, they include the natural period of vibration, the ductility, the seismic coefficient, the base shear, and all the numbers that engineers just love to talk about and to think about. And there's information on the design of each of the elements. And all these numbers mean a lot to engineers, but to architects, of course, that they're meaningless. But that doesn't matter, the engineers are happy. And so I think on that note, I will close my lecture and just invite discussion and questions. Thank you.
Nije potrebna moderacija, ako možete da postavite pitanje na engleskom ukoliko ima problema prevešćemo, ali pretpostavljam da većina ili svi znaju. Andrew posebno je želeo da časom da razgovara i da studenti postavljaju pitanje ili bilo ko iz publike, tako da nemojte se stidite, slobodno postavljate pitanje. Tako da se interesujete.
Svetlana, maybe some people might like to ask in Serbian, and you can translate.
Yeah, I offered that.
Oh,
Yeah.
okay, lovely. Yes, please.
Can we import our own models into this program or not?
I don't believe you can. But I just perhaps need to check. No, we can export, but we can't import. But remember, this is just for preliminary design. So you make your model just to approximate your final design. And so it doesn't need to be very incredibly accurate. It's for preliminary conceptual design. And so you can take, you can make quite a rough model, but you'll still get quite accurate results. Yeah, so that's a really good question. And perhaps I should also say this software only runs on a PC. It doesn't run on Macs.
On Windows.
Windows compatible, yeah.
I just want to ask, do the plans have to be identical on all levels, or can they vary around floors?
They have to be identical in the model. And so usually, when we are modelling a real building, we have to fit all the input. So if say half of the floors of your building were smaller than this, then we would model the whole building to be a bit smaller. And so we have to just use our intelligence to make the transition from the real building to this rather simple model. And another example of its limitations is that it assumes that every story is the same height, you know? And so if that is not the case with your building, you might take the average story height, you know, and use that. And so we have to make these simplifying assumptions in order to use such a simple model. Yeah.
Is it possible to model circular shapes or just?
By making a 16-point polygon. That's the closest we can get. But you know, that will give you very accurate member sizes for your final design. It'll be close enough. So it's very simple software, isn't it?
More questions?
So what's the soil on this car advanced?
Oh, there's an advanced section here. This tab here. This is quite funny actually, because my co-developer is a really tough structural engineer. I'm a rather soft engineer because I've worked for 30 years in a school of architecture, and I'm rather confused as to whether I'm still an engineer or I'm partially an architect. I don't quite know. But anyway, my colleague, he is a civil engineer, and he wanted this tab because he said that the engineers, they might want to investigate the stiffness of the foundations, because you know, the stiffer the foundations, the less the natural period, and therefore the greater the seismic design force. And so we've got this tab because resist assumes like ordinary foundations. We assume that the foundations are not rigid. But there's this option for you to specify rigid foundations. And actually most engineers assume that, don't they? Unless it's a very soft site. You know, for a low-rise building, we would assume the foundations are rigid. But this gives an engineer the opportunity to investigate what happens if you have ordinary foundations, and what happens if you make them stiffer by a factor of 2 or 4. You know, what influence does that have on your design loads? And this is a tab that architects never want to go near, but engineers might have fun with it.
Can we have a brief about the next lecture? Just anticipation of the
Next lecture.
I can read you.
Sure.
I believe everybody has received the lecture today for today's PDF document, and on Saturday you will receive before the lecture. It is going to send you the lecture for Saturday. But
so these are the titles for the next lecture. I'm going to take you through the problems that we encounter in real buildings, particularly in terms of penetrations in our floor slabs and so on. And I'm going to look at these common problems and give you solutions to overcome them. Because, for example, many times architects want to have large atriums in their buildings, and that can cause great difficulty in ensuring good seismic performance. And so I'm going to give a number of different solutions to these problems. And in my third lecture, I'm going to talk about vertical structure, the common problems that architects encounter and cause. And in fact, many of the problems have been caused by Le Corbusier and his principles. And I'm going to show you how to overcome those. How to maintain them architecturally, but achieve a building that will perform well in earthquakes. So these are basically what I'm going to talk about in my next 2 lectures.
Okay, any more questions? Još pitanje? Okay. U tom slučaju, in that case, let me say this in English. We would like to thank Professor Charleson for giving this very interesting lecture. I hope that everybody is going to try resist by Saturday and come up with questions. And right now there is going to be a cocktail for half an hour or so in front of this room. And on Saturday, just notice that the lecture is going to be at 11 o'clock, and it is in a different room. It's 254, not this one, which I think is down on the other side of the corridor. That is just an announcement, and you will get a lecture in electronic form, not printed, mostly same as today. So thank you very much for coming, and let's thank Professor Charleson and have opportunity to talk to him during the cocktail.